Hello, and welcome to the presentation of our study on whole-body lesion detection and prostate cancer staging in gallium-68 PSMA-11 PET-CT using deep learning. PSMA ligand PET-CT has shown high accuracy for prostate cancer staging. Nevertheless, accurate interpretation of PSMA-targeted PET-CT can be challenging, with possible tracer uptake in sub-milliliter lesions as well as known pitfalls. We developed and evaluated a deep learning method to detect lesions in the whole body in gallium-68 PSMA-11 PET-CT and classified them according to a standardized staging framework. Gallium-68 PSMA-11 PET-CT images of 93 patients with proven prostate cancer were annotated by two expert physicians. Images of 43 consecutive subjects referred to PSMA ligand PET-CT for all indications of prostate cancer were annotated by the first reader and used for training a deep learning network. Images of 50 consecutive subjects referred to PSMA ligand PET-CT for primary staging or for assessment of biochemical recurrence were annotated by the second reader, of which 20 were used for training and 30 were used exclusively to evaluate the network performance. For all subjects, each region of interest with increased tracer uptake was segmented by the expert reader, labeled as physiological or suspicious, and assigned an anatomical localization from a set of physiological uptake sites and sites relevant for staging according to the PROMIS framework. We then used PET-CT images and expert labels to train a convolutional neural network, in short CNN. The CNN is trained to evaluate regions of interest of the PET-CT, classify them as either likely physiological or suspicious uptake, as well as assign them an anatomical location. To perform this task, the network evaluates multiple inputs, including the PET-MIP, together with the PET and CT multiplanar reformations and atlas coordinates derived from the region location. We used transfer learning by employing a network developed for the same task on more than 600 FDG scans and fine-tuning it with PSMA ligand PET-CT training data. In addition, we performed data augmentation by applying image deformations and by adding to the training data regions with lower physiological uptake that were not originally labeled by the experts. We evaluated the CNN performance with multiple automated processing steps, as illustrated in this example subject from the top left to the bottom right. First, we used the CNN to classify all regions of interest with uptake above the blood pool level. Second, we selected regions that were classified as suspicious together with their anatomical localization assigned by the network. As a third step, we assessed the CNN detection performance compared to expert labels by evaluating the fraction of suspicious sites successfully detected per subject, or sensitivity, and the number of false positive sites identified per subject. Finally, to assess the CNN anatomical localization performance, we evaluated the ability to predict the MIN0 or MIN1 stage, as presence or absence of suspicious pelvic nodes, and MIM0 or MIM1 stage, as presence or absence of lesions in extrapelvic lymph nodes, bone, or other organs. In total, around 2,900 regions with elevated uptake were annotated by the expert readers, of which 570 were suspicious regions, including pelvic lymph nodes, distant lymph nodes, bone lesions, and other organs. The median segmented volume of suspicious lesions was 1.2 ml, with an interquartile range between 0.6 and 2.9 ml. The CNN showed good ability to detect suspicious sites, with 84% average sensitivity per subject, and a median of 2.5 false positives per subject. Based on the anatomical localization of regions determined using the CNN, MIN0 stage was correctly predicted in 18 out of 22 subjects, MIN1 in 8 out of 8 subjects, MIM0 in 2 out of 5 subjects, MIM1 in 25 out of 25 subjects. The following slides show examples of subjects in the test set, for which the PET maximum intensity projection is shown on the left. The CNN labels are overlaid to the PET MIP in the center, while expert labels are shown on the right. In the first example, the CNN was able to identify suspicious regions in good agreement with the expert visual assessment. On the other hand, the improper classification of the anatomical localization determined an incorrect definition of the M stage. In this second example, the CNN identified a single distant suspicious region in good agreement with the expert evaluation. In conclusion, the investigated deep learning method showed promising results for the detection and anatomical localization of suspicious uptake sites in the whole body in gallium-68 PSMA11 PET-CT, including sites with small volume. The anatomical localization is shown to have utility in providing staging support for prostate cancer. Thank you for your attention.